Now, in the following, I outline a very simple framework where I extend the Solo model to include automation. This follows a paper that I've published in 2019 in Macroeconomic Dynamics. And first, we start with a production function where output is produced using labor with an output elasticity of 1 minus alpha and physical capital with an output elasticity of alpha. So that would be the traditional Cobb-Douglas production function that we have here, right? But now we change this production function in a way that it actually resembles this type of production process here. So what we do is we include another production factor that is in essence physical capital, but it substitutes for the workers. And these are the industrial robots. So everything in this production function is standard except the industrial robots, which are in their nature physical capital in the accumulation process. So people have to invest to build robots, right? But in the production process, the robots substitute for the human workers, and therefore this shows up as a sum. Now, this is the simplest way you can introduce the robots. Of course, in reality, you would have a relative productivity between humans and robots. So you would have productivity multiplied by the human workers, so labor augmenting technological progress. And then you can have robots augmenting technological progress that multiplies with the stock of robots. Then you can have all different kinds of substitutability between low-skilled workers and robots, or between workers in general and robots. Here we assume perfect substitutability. However, nothing of the more realistic aspects here would change the general prediction. So if you have imperfect substitutability, then as long as robots are a comparatively good substitutes for workers as compared to physical capital, the results would still hold true that we discuss now. Now, the first thing to recognize here is that the diminishing returns with respect to physical capital are overcome by the introduction of industrial robots. We see this here because in the standard model, what you have is if you add more and more assembly lines without changing the number of human workers, you cannot you can produce more, but at a diminishing rate, right? At some point, adding more assembly lines would not really increase your output anymore. However, with another type of physical capital available that can substitute for the workers, you can build new assembly lines and then stuff them with industrial robots. So you would still not increase the number of workers, but you would not run into the diminishing returns of capital accumulation because you can overcome it by employing robots instead of human workers. And then the interesting thing, and that's the first central prediction of such a model, it happens that even within a solo model, without any technological progress, without any labor augmenting technological progress, you would have perpetual long-run economic growth becoming possible. So it depends on the saving rate and so on, whether you really achieve perpetual economic growth. But if you are in a parameter setting where it is possible, then the economy would grow in the long run with a positive growth rate along the long-run balanced growth path, even without any technological progress. So this introduction of automation changed one of the crucial predictions of the Solo model. It now becomes possible to have long-run economic growth without any technological progress. And the rate of economic growth in the long run would be a function of the saving rate. So the more the country invests, or people in the country invest, the faster would be economic growth. And it depends negatively on population growth and the rate of depreciation. And these two aspects hamper per capita capital accumulation. So it's intuitively clear that they slow down economic growth in the long run, while everything that increases investment, the saving rate here, would increase economic growth in the long run. So the bottom line here is that perpetual economic growth becomes possible even without technological progress, where automation then acts as a driving force of economic growth. And this prediction is in line with empirical evidence. Gretz and Michaels have shown that automation increases productivity and economic growth, and others have shown this as well. So indeed, automation would be a factor that increases overall what we can produce. So on average, it would have positive output and income effects. But that, of course, does not mean that everybody will benefit. That's what we will turn to next. So we can still stay in the same framework, but now we focus on the factor rewards. We know the wage rate will be given as the marginal product of the production factor labor, so that's the derivative of the production function that we had here with respect to L. And the interest rate would be the derivative of the production function with respect to K minus the rate of depreciation, right? So these would be the factor rewards in the economy. As compared to the standard factor rewards in a standard Solow model with a Cobb-Douglas production function, we have a difference, namely that the stock of robots shows up in these two expressions. The wage rate usually would increase with physical capital, because if you have more assembly lines, you also need more workers to staff them. But here the stock of robots has the opposite effect. The stock of robots means that you have more competition with labor, and therefore there would be a downward pressure on the wage rate. So the stock of robots has the opposite effect than the stock of traditional physical capital in such a setting. And with respect to the interest rate, it's the other way around. So here, if you have usually more traditional physical capital, so more assembly lines for a given number of workers, that would put downward pressure on the rate of return of physical capital. So that would put downward pressure on the interest rate, right? So that's what we see here. However, if you have robots, this other type of physical capital that you can use to substitute for the workers, then there would be an upward pressure in the interest rate. So the bottom line here is that wages are increasing with traditional physical capital, but decreasing with automation capital P. And now we can also compute the labor income share, which is the wage rate that we've just derived multiplied by the number of workers. That's then the total wage bill in the economy divided by the total value of production, so aggregate GDP. So that would be the wage bill divided by aggregate value added is the share of income that goes to the production factor labor. In the standard Solow model with a Cobb-Douglas production function, that is always equal to 1 minus alpha. Alpha is a constant, so irrespective of what happens in the model economy, you can never change the labor income share here. So if you accumulate capital, or if the number of workers changes, or so on and so forth, the labor income share would still be a constant 1 minus alpha. And that was also why the Solow model was so successful, actually, because it was able to predict a constant labor income share, which was a stylized fact of economic development until the 1980s. So the labor income share was constant in the long run. The Solow model was consistent with this stylized fact, and other economic models were not consistent with this stylized fact, such as an AK growth model or the Harrod-Domar growth model. However, since the 1980s, the labor income share is decreasing. Now, what does our framework tell us about the labor income share? If we compute it, then we get the 1 minus alpha, but then multiplied by the number of workers, divided by the number of workers plus the number of robots. So as long as the number of robots is 0, we are exactly in the same situation as in the standard Solow model, so L over L cancels out and we have 1 minus alpha. So until the 1980s, this model would also predict a constant labor income share, because the number of robots, as we've seen in the first part of this course, was negligible until the 1980s. But since the 1980s, the stock of robots has increased quite strongly, so this would increase from 0 to a positive number, and we would observe a decrease in the labor income share. And that's exactly what we see in the data. So this model, where we augment the Solow framework with automation in terms of industrial robots, can also explain a decreasing labor income share since the 1980s and a constant labor income share before. So to summarize this, automation in such a setting would reduce the labor income share, and this is again in line with empirical evidence, for example by Karababunis and Neiman, or by Eden and Gackel, who show that automation indeed empirically reduces the labor income share. So up to now, we have really had a very simple framework, right? So it was just a solo model extended by another production factor without any bells and whistles. Now we want to extend this framework so that it becomes a little bit more realistic, and we can also analyze other aspects such as wage inequality. So the first thing by which we augment the model now or extend the model now is to allow for low skill and high skill workers, where we denote low skill workers by LL and high skill workers by LH. And we assume an imperfect substitutability between low-skilled workers and high-skilled workers that is determined by gamma. So gamma determines the elasticity of substitution between low-skilled and high-skilled workers. If gamma is negative, then the two are complements, cross complements. If gamma goes to minus infinity, we would have perfect complements. When gamma goes to 0, we would have a Cobb-Douglas structure, and gamma in between 0 and 1 would mean gross substitutability between low-skilled and high-skilled workers, and only if gamma is equal to 1, we would have perfect substitutability. This production function follows a paper by Lankish and co-authors, where we augment the solo model to account for these two types of workers in order to be able to analyze the effect of automation on the skill premium or on wage inequality between low-skilled workers and high-skilled workers. To achieve this goal, we would need to compute the wages of high-skilled workers and the wages of low-skilled workers. So again, we would have to take the derivative of the production function with respect to LH to get the wage of high-skilled workers, and then with respect to LL to get the wage of low-skilled workers. The resulting expressions, however, are quite complicated, so I do not repeat them here. They would require perhaps 2 or 3 lines. But what we are really interested in is not the wages in absolute terms, but in relative terms. So the wages of high-skilled workers divided by the wages of low-skilled workers, which is actually the skill premium. It's the extent by which the wages of high-skilled workers are higher than the wages of low-skilled workers. So if this is greater than 1, we have a skill premium, and the size of the skill premium is the extent to which this ratio is greater than 1. Now, the good thing is that even though the expressions for high-skill wages and low-skill wages are quite complicated, if we take these derivatives here with respect to LH and LL, they contain some parts that are the same, that you can easily see, because what you have to do when you take the derivative is first to take the outer derivative and have the expression within the square brackets unchanged and so on. And that's the same in both high-skilled and low-skilled workers wages, and therefore if we divide the two, a lot drops out actually. And what we are left with is then just a very simple expression. We have 1 minus beta, where beta is basically the share of low-skilled workers in the total labor input in this CS production function here, divided by beta. So that's just a function of the parameter beta. And then we have to multiply this by the amount of industrial robots plus low-skilled workers divided by the high-skilled workers. Here we assumed that the low-skilled workers can be substituted directly by the robots. So these are the assembly line workers, the low-skilled workers, basically. So that's the interpretation here. And they can be substituted by the robots. However, the high-skilled workers here cannot be substituted by the robots. These are the engineers, scientists, managers, and so on, that are more complementary to robots. So they cannot be directly substituted for by robots. Indirectly, they can be substituted for by robots, because low-skilled workers can substitute for the high-skilled workers here, although imperfectly so, right? Now, if we look at the skill premium, however, what we see is the stock of robots enters this expression, and the more robots we have, the higher would be the skill premium. So an increase in the stock of robots would imply that the skill premium goes up. It pays off more to invest in higher skills, because the extent to which wages of high-skilled workers are higher than the wages of low-skilled workers increases with automation. How does this square with the empirical evidence? Now, what we have here is the US data in terms of the skill premium. That's the dashed line here. we observed that the skill premium was basically, in the notation that we had on the previous slide, was 1.7. So that means that the wages of high-skilled workers are 70% higher than the wages of low-skilled workers in the 1970s. Then until the 1980s, not much changed, but then since then, the skill premium has increased quite strongly. And here at the end of this sample, which is 2015 here, we had a skill premium of 120%. So the wages of high-skilled workers were more than twice as high as the wages of low-skilled workers in the US. Now, what the model would predict is the solid line here. So a low skill premium in the 1970s, when there were almost no robots, and then a continuous increase in the skill premium with the increase in the number of robots in an economy. So again, during the 1980s, when robots started to accumulate, the skill premium increased, and that's also what the model predicts. So the predictions of the model are in line with the stylized facts with respect to the skill premium. But as you see here, the model over-predicts actually the dynamics. So we have a stronger increase in the skill premium implied by the model than we observe it in the data. And there are several reasons for that. One of the reasons is that in our model, we assumed that the number of low-skilled workers and the number of high-skilled workers, they are kind of exogenously given, so you cannot become a high-skilled worker once you're a low-skilled worker, right? So we don't have endogenous education. What you observed in reality was that also the share of high-skilled workers increased, and that would lead to a downward pressure in the skill premium because you have more high-skilled workers and fewer low-skilled workers. So the marginal product of high-skilled workers would decrease and the marginal product of low-skilled workers would increase, ceteris paribus, in such a setting, and that's not allowed for in our simple framework. And the second thing is that, of course, you may not have a perfect substitutability between low-skilled workers and and robots, but an imperfect substitutability, and then this skill premium would also increase by less if the stock of robots increases. However, the interesting thing is that even this very simple model gets the stylized facts quite right and gets the main dynamics right. So to get first insights into how automation may affect the skill premium, it's not a bad way to start. So the bottom line here is that automation raises the skill premium and therefore wage inequality. And again, this is in line with empirical evidence. So Gretz and Michaels have shown that robots increase wage inequality. Acemoglu and Restrepo have shown this, and many others as well. So the simple framework that we had here is able to predict the stylized facts. Now the next item on the list of what automation implies for the economy was the employment effects. Up to now, we didn't have employment effects because labor supply was inelastic, as in the standard framework, in the standard neoclassical framework, and it was just that the wages adjusted and people were assumed to work for whatever wage there is in equilibrium. Now we analyze what happens actually to unemployment in such a situation. And there are many different ways of introducing unemployment in such a setting. The first one is perhaps the most straightforward one, that is to just introduce elastic labor supply so that people observe the wage rate, and when the wage rate falls, say due to automation because there is competition with robots, then they may also decide that the wage rate is then lower than the reservation wage and therefore they reduce employment or stop working altogether. So then we would have the possibility of voluntary unemployment in such a setting, as we show in a paper with Holger Strulik in 2017. So there would be downward pressure on the wages, particularly for the low-skilled workers, and the wages may end up below the reservation wage, and then people would decide endogenously to quit work in such a setting, and we would have voluntary unemployment. However, this may not be the most interesting type of unemployment in this setting, and it's also not what we are usually concerned with, or what the media is concerned with, or policymakers are concerned with when they talk about the economic consequences of automation. There we are rather interested in involuntary unemployment. Now what we show actually in the same version, in the same paper, but in the published version, is that automation can also be responsible for technological involuntary unemployment if you have aspects of efficiency wages baked into the whole production structure. So in this case, the wages would be higher than the equilibrium wages to induce more effort among the workers. This could be, for example, because you want to pay them such that they are not shirking and so on, or you pay them higher because you are concerned about effects of fair wage constraints, so that low-skilled workers observe the wages of high-skilled workers. The wages of high-skilled workers increase tremendously, but their own wages are stagnant or even decrease, and then they don't perceive the situation as fair and exert less effort and so on. And to instill more effort, you pay them a higher wage than the market clearing wage. And in this case, there would be equilibrium unemployment. In the second case that I said, with fair wage constraints, there would be involuntary unemployment among the low-skilled workers. And if automation increases, this involuntary unemployment would increase as well. So in this case, a model with efficiency wages and automation can explain involuntary unemployment. However, there is also another different way of modeling employment in macroeconomics, a very prominent one by Mortensen and Pissarides, who model frictional unemployment. So the search and matching type of model of the labor market has equilibrium unemployment, but that is a frictional unemployment because you have churn in the labor market, so firms shut down at the same time other firms are established, and you have that the firms search for workers and the workers search for employment opportunities, but everything takes time and there are certain frictions, and therefore in equilibrium you will always have a certain level of unemployment that is due to these search and matching frictions. Now it turns out that if you take such a search and matching model of the labor market with low-skilled and high-skilled workers, where low-skilled workers can be substituted for by robots, then actually automation reduces the search costs for firms, and that increases efficiency in the economy and promotes firm creation, which could actually even lead to a situation in which the equilibrium frictional unemployment decreases due to automation. So what we show in a paper with Dario Kortz in 2021 in Oxford Economic Papers is that the low-skilled workers would be substituted for by the robots, but at the same time that would increase efficiency of matching, so high-skilled workers would benefit in terms of employment opportunities, and under certain circumstances, depending on the parameter values and therefore on the setting of the country that is under consideration, it could be that the number of low-skilled workers who lose their jobs is much less than the number of high-skilled workers that gain jobs in equilibrium. So you could have a reduction in employment overall due to automation. And that holds true particularly when you allow for endogenous education, where some low-skilled workers may be tempted to increase their skills, may invest in education to become high-skilled workers when they observe that they are substituted away by robots. So if you have this endogenous education, then this would even boost employment opportunities overall and lead to a situation where it is more likely that aggregate unemployment decreases with automation. So the bottom line here is that the effects of automation on unemployment are not clear-cut from a theoretical perspective. We have seen that there are many possible results. We could have increased involuntary unemployment due to efficiency wage channels, but we can also have reductions in unemployment through search and matching friction channels. But we can also have increases in unemployment through the same channels, so it depends a lot on the underlying country setting. Now, the interesting thing is that this is again consistent with the empirical evidence, which is also kind of inconclusive on the employment effects of automation. For example, there is this famous paper by Acemoglu and Restrepo from 2020, who find negative employment effects of automation for the United States. But Dowd and co-authors apply the same method to Germany and find actually negligible effects on unemployment in Germany. And some other studies, such as Gregory and co-authors and Mann and Büttmann, find even positive effects. So you have that employment increases due to automation in this setting. And now we can again say, well, it depends a lot on the country characteristics, and that's the same what the theory tells us. So now we've talked a lot about the effects of automation on economic growth, inequality, the labor income share, and employment. But we did not talk that much about artificial intelligence yet. So automation was up to now conceptualized as being industrial robots. But automation by artificial intelligence is quite different from automation in terms of industrial robots. The reason is it affects mainly cognitive work. So it affects mainly the high-skilled workers actually. So what we did in a paper with David Bloom, Jamel Sadawi and Mario Veroete was to introduce a production function that incorporates both industrial robots and artificial intelligence. So what we have here is output is again produced with physical capital with an output elasticity of alpha. But then this labor type of input consists of different parts. We have the low-skilled workers that we denote by LU, or unskilled if you will. And we have the high-skilled workers, LS. And now what we have is that the robots, the industrial robots, are substitutes for the low-skilled workers, but imperfect substitutes. The elasticity of substitution is determined by theta. And the high-skilled workers can be substituted for by artificial intelligence that we denote by G, for ChatGPT or whatever. And the elasticity of substitution between high-skilled workers and artificial intelligence is determined by this phi parameter here. And overall, we again allow for substitution between low-skilled and high-skilled tasks, which is determined by gamma, as before. Now, this production function is a double-nested CS production function, and it allows for a lot of different possibilities in terms of substitutability of the different production factors. So it's quite general, but what we say, what would most likely be the case is that industrial robots are a better substitute for low-skilled workers than artificial intelligence is for high-skilled workers, at least up to now. The reason is you can substitute the low-skilled workers directly with the robots, while for the tasks that high-skilled workers perform, you still need some form of human supervision. So if artificial intelligence can diagnose diseases, you still need the doctor to interpret the final result, to talk to the patient, and so on. In terms of computer coding, although there are algorithms already capable to write functioning computer code or very sophisticated computer code, very often you still have to have some human supervision and to adjust the code and so on and so forth. So that's the reason why perhaps the substitutability between low-skilled workers and robots is higher than between high-skilled workers and AI. And the next thing is even more crucial. What we think is that the high-skilled workers can be substituted for by artificial intelligence more easily than by low-skilled workers. So that's again very intuitive. For example, it's almost impossible that a low-skilled worker can write computer code or diagnose diseases or translate texts or so. So you really need a lot of skills, actually a lot of education to be able to perform these tasks that artificial intelligence can perform quite easily. So I think this assumption is very unproblematic in terms of intuition and in terms of empirical evidence, but it drives the results in a crucial way. So as we will see in a moment. So if we now compute again the skill premium, in this case the wages of skilled workers divided by the wages of unskilled workers, then we get a more complicated expression than before in the case of the model where we only had industrial robots, but the results are again very intuitive. What we would have here is that the use of industrial robots basically would increase the skill premium, usually for the substitutabilities that are kind of as we had discussed it before. So in this case, we would have an increase in the wages of high-skilled workers as compared to the wages of low-skilled workers. But with respect to the increase in artificial intelligence, it's the other way around. So here we would have that actually this term here is negative because the artificial intelligence is a better substitute for high-skilled workers than low-skilled workers are for high-skilled workers. So that means that this term here is smaller than 1, and since we subtract 1, the exponent is negative, and that means that artificial intelligence would reduce the skill premium. And the threshold where the use of AI is neutral in its impact on the skill premium is when gamma over phi is equal to 1. As I said before, however, the intuitive range would be of the parameter values that gamma is smaller than phi, and therefore this exponent is negative, and artificial intelligence indeed reduces the skill premium. Why is this the case? Well, it substitutes for the high-skilled workers, but this increase in the amount of kind of production that you have through the high-skilled workers does not impact on the low-skilled workers by the same amount, right? Because they are not as easily substitutable than high-skilled workers are by artificial intelligence, and therefore there would be a downward pressure on the skill premium. Now, is this consistent with empirical evidence? I would say the jury here is still out, but some papers have found indeed this effect, right? So that AI reduces the gap between low performance and high performance. Basically, if you have the same tasks, because the low-skilled workers can benefit in this case much more by artificial intelligence than the high-skilled workers. That would be perhaps one type of evidence that points in this direction, but I would say in general we do not yet know. So we are in an early stage of deployment of artificial intelligence, so we have not really seen this aggregate data that we can use to test this hypothesis, but some early evidence suggests that indeed this is the case. So now we can come to the conclusions. Automation leads to rising productivity and income. I think that was across all the frameworks that we've discussed, and it's also supported by empirical evidence, so we can be rather sure that this is indeed the case. It also implies a declining labor income share. We've seen this for the use of industrial robots. I've not derived it here explicitly for the use of AI, but if you use the framework that I've proposed at the end with this production function, what you get is a decreasing labor income share. And that's also what we find empirically, for example, in the paper with Francesco Venturini and Antonio Miniti on how the labor income share reacts to artificial intelligence. Then you would have rising wealth inequality because capital actually has different forms now, but those who benefit from the income that artificial intelligence earns or that robots earn and so on, this income goes to the capital owners. And the people who do not own capital, who do not own wealth, they would not earn this income. So wealth inequality is likely to rise with automation. And then we have seen that there is a change in income inequality depending on the automation technology. So industrial robots are more likely to increase the skill premium, and artificial intelligence is more likely to decrease the skill premium. And overall, we've seen that the employment effects of artificial intelligence and industrial robots, that's still unclear from the theoretical perspective as well as from the empirical perspective. What could be potential policy levers that could help us to mitigate the negative effects of automation, support the positive effects, and so on? So one is definitely raising abilities. So educate the people, invest in education, invest in retraining for those who get unemployed because of automation, and so on and so forth. So this will help quite a lot, but of course it's not a silver bullet. So we may have the situation that particularly with automation of cognitive tasks, that education also does not really help, because then just a few years later the new tasks that you learned also become obsolete. But it's one important lever. Another important lever may be wider capital ownership. So that would allow also those who are poorer or who may suffer due to automation because of unemployment or because of lower wages to participate in the positive effects of automation through the wealth income, through the asset income, the capital income that these new technologies generate. That's nicely said, but it's much more difficult to be done. How do you ensure that everybody has a stake in wealth of the economy? So do you redistribute it? What happens after you redistributed it? So people in principle could sell assets that they get from somewhere immediately, and then you would not have gained anything, and so on and so forth. So that's kind of an interesting aspect, but it's difficult to achieve in reality. Another aspect is taxation, of course. So at the moment, we have the large part of taxes is tax income. So tax revenue is determined by labor income taxes. And of course, that's a little bit strange because labor is now coming under pressure through automation. Nevertheless, we tax it at a very high rate, and automation itself is not taxed. So some have argued, yeah, we have to introduce robot taxes and all these kind of things. But in the literature, we have shown that robot taxes may not be the best idea because they actually would hamper automation, which is on average a good thing. So we have rising productivity, rising income, rising welfare due to automation. So perhaps there is another way of getting positive effects. On top of that, it's not clear how you tax automation. So you may be able to tax a robot, but how do you tax artificial intelligence? How do you tax ChatGPT? Do you tax each and every single query and so on? So that's just impossible legally and practically, basically. But what would be possible is to reduce labor income taxation by introducing other taxes or increasing Pigouvian type of taxes such as environmental taxes. So tax CO2 emissions and so on, and use the revenues of that to reduce the taxes on labor would be one aspect to move in a positive direction, because pollution and CO2 emissions are anyway a bad thing that we want to reduce. So it would be straightforward to tax it at a higher rate and use the tax income to reduce some other taxes that are harmful for economic growth. Or another way would be to tax land, for example. Land cannot move to another country. Capital, if you tax capital, then capital is very mobile and it can easily kind of move, or people could decide not to invest that much anymore, all things that we do not want to have. But if you tax land, that's less of a concern. In addition, if you have environmental taxation, this may act as a substitute for robot taxes to some extent, because robots and artificial intelligence at the moment, they need a lot of electricity input. And electricity generation is still to a large part an activity that generates CO2 emissions, so based on fossil fuels. So if you tax that, you can indirectly tax automation in a way that is legally and practically possible by having such environmental taxes. And finally, we could have a system of a progressive consumption tax that's nicely described by Robert Frank. Because what a consumption tax is, it is quite efficient. But on the other hand, the problem with the consumption tax is that low income households pay a larger share actually of their income. So the tax is regressive. Why? Because consumption is taxed at a flat rate, and consumption is a greater share of income in low income households than in high income households. So the total amount of taxes as a share of the total income paid is higher by low income households than by high income households in case of the consumption tax. What Robert Frank says, however, is that we could design a consumption tax in a progressive way. How? You would have that at the end of the year, you don't report to the tax office your income and what you consumed that is tax deductible, and then the difference would be your taxable income. But instead, you report your income and your savings, and then the rest is consumption, and you could have progressive rate applied on this amount of consumption. This would have additional advantages because it would induce kind of a little bit of honesty into the system, that you really report your true savings. Because if you don't report your savings, or if you put your savings to a tax haven and so on, that would actually increase your tax so your taxes that you have to pay. Because if you report less saving, your consumption would be higher and you would have to pay more taxes. So it would not pay off anymore to kind of hide your capital, your wealth income from the tax authorities in a tax haven or anywhere else, right? So that would be an additional benefit of such a progressive consumption tax. And then you can use this income from the tax to reduce labor income. So there are many different possibilities and policy implications that one can think of. I think the important point is to get these these processes started, to think about that kind of stuff. And therefore I just say thank you for your attention.